Okay, awesome. Hello, everyone. I'm Aditya. As I said, I work with Professor Neil Lawrence, and I'm working on probabilistic perspectives as part of my PhD. I'm in my second year now, so most of this work is the main PhD project that I've been interested in for about a year and a half. And I'm also going to touch on just like other things that I'm also looking into. So my main interest is probabilistic interpretations of dimensionality reduction methods, mainly applied in single-cell biology. And just before going to DR, I will try to motivate why I think probabilistic interpretations can be really interesting. So very briefly, so when I say probabilistic interpretation, what I actually mean is there are lots of algorithms out in the wild that take in data, process, and check out something of interest. And in a lot of cases, we can interpret these algorithms as inference algorithms corresponding to proper probabilistic models. So a probabilistic model would be a collection of random variables and distributions linking them in interesting ways, where we can specify interesting prior information that is available to us at the outset, depending on whatever problem that we're tackling. And then the inference for the object of the stuff that we're interested in happens through standard probabilistic inference. So stuff like MAP estimation, maximum likelihood estimation would be one of them. Trying to sample from the posterior of this distribution might be another way one can do inference. So really what I'm interested in is this interpretation of algorithms as inference algorithms corresponding to probabilistic models. And on this slide here, I have like 4 examples of why I think these things are actually very interesting to look at. And it's also like a shameful plug into some of the other work that I've been up to. So these are like side projects that have been submitted to like workshops, basically. And in each of these cases, we've found that interpreting classical algorithms as part of interesting scientific problems can actually lead to very interesting outcomes. So for example, in the first project, we were looking into the interpretation of random effects models, which are frequentist versions of hierarchical models, essentially. So these are linear models where there are some latent variables like corresponding to different intercepts for different groups, stuff like that. And in this project, we interpreted random effects models as part of dimensionality reduction methods to be Gaussian processes, which just allowed us to use standard Gaussian process scaling ways to make this like super efficient and scale to millions of data points. It also allowed us to put in really interesting prior information, which I will talk about in a little bit. In the second example, we are looking into the equivalence between GNNs and graph kernel feature functions to see if these can be useful for downstream applications like Bayesian optimization, especially in contexts where the GNNs might be learning interesting representations of uncertainty when pre-trained on molecular data or protein data, for example. In the third project, this was a case study of interpreting generalized additive models, which are linear in the parameter regression models, basis function regression models, which can be interpreted as GPs when you use appropriate basis functions, which allows us to utilize pre-fit GAM models, for example, coming out of MGCV, which is a very, very popular R package that is used in bioinformatics to fit such models, but port them over to your favorite like Gaussian process library in Python, for example. And the fourth example shows an interpretation of dynamic time warping as a hidden Markov model. And what this enables is really interesting posterior inference over stuff that we might care about, where there is missing data, if there is weird like data sampling going on or irregular sampling of data going on, or if there are scientific constraints that lead to weird posterior uncertainties. Is really like just inference, probabilistic inference allows us to understand exactly what it is that that our scientific constraints mean in these domains. And yeah, as I mentioned, most of this work is published as a preprint or in workshops. So if you're interested, do let me know. I will happily send you a link. So getting into dimensional reduction. So DR methods are essentially methods that take in high dimensional data and compress it to a low dimensional space. So in most cases, you would be working with a large matrix of many columns where each row in this matrix represents an independent observation of some high dimensional data point, that we're interested to project to a low-dimensional space. And the key idea behind DR is that in a lot of cases where we do have such matrices, it's hypothesized that these things lie on some low-dimensional manifold. And this really comes from the idea that most of the times when you're measuring these large matrices, there's actually only a few factors that lead to those numbers that you see in those matrices being expressed in a certain way. So an example of such a matrix can be like a bunch of images where every column corresponds to pixel values at different locations in an image. Or for example, it can be gene expression data where every column corresponds to the expression of a certain gene in a cell, and there's 20,000 cells in the human body, and where every row corresponds to an independent observation of gene expression in a certain cell, essentially. And in that example, in that single cell example, it usually happens, usually turns out to be the case that there are a few biological effects and maybe a few other technical effects, as I call them, that governs the gene expression that we actually observe. And we don't really need 20,000 numbers to represent what's actually going on inside the cell. So as an example here, on the left, I've plotted 3 genes that are expressed cyclically when cells divide. So cells divide all the time, and this is a cyclical process. And there are a couple of genes that are really strongly expressed as a function of where the cell is in this division cycle. So really, the thing that really determines the level of expressions of these 3 genes is just where the cell is in that cycle. So really that one state can really represent a lot of the information that you see in your gene expression matrix. But alas, we never really see this information. And what we see is this. We see the joint expression of a lot of genes, but we never directly observe what state the cell is in, for example. And really trying to recover these hidden states from information like this is what DR is all about. And as an example here, you have like a 3-dimensional space of expression for 3 genes, but you can see that the mean expressions of these cells really lies along a 1-dimensional manifold. In this case, a circle, because the information is cyclical. Okay, so again, to just motivate this project a little bit more, I'm very interested in looking at applications of dimensionality reduction in single-cell biology, because practically every sort of workflow in single-cell biology takes in a large matrix of gene expression, compresses it down to a low-dimensional space, and then does something interesting with it, like clustering or pseudotime identification or trajectory inference or differential expression analysis and so on. And probabilistic approaches to dimensional reduction in the space are actually very interesting because A, there's a lot of noise in the data, and B, a lot of interesting information might be available at the outset. So as an example, and this kind of connects to the first project that I was mentioning, we know that certain genes are expressed in a cyclical way, given a cell state. So we can essentially define a GP with a periodic kernel to really represent that form of information. Another example might be if you have different cells sampled from the same area of space, you might think that the expression of those genes would be highly correlated as opposed to cells which are sampled from two very, very different parts of the body. And we might really be interested in interesting biological effects that are driving gene expression, as opposed to these like weird confounders like cell state and the spatial information with which the cells sort of correspond to. And so probabilistic approaches can really help us narrow down and identify latent variables that are meaningful, that are scientifically meaningful in the context that we're interested in for the use cases that we're interested in. So really the main sort of idea for this project was, can we identify what models these other DR algorithms that are used in single-cell biology correspond to, so that we can put in interesting prior information and recover identifiable latent variables and do interesting science with them, especially because they're so extremely prevalent in these workflows. By the way, do stop me for questions anytime. Like I don't have a lot of slides, so happy to talk. Okay, so a quick background on probabilistic dimensionality reduction. There are quite a lot of algorithms that are known to have either probabilistic interpretations or have been set up in such a way that they are probabilistically motivated. So basically, everything that you see on screen there fits into this very nice setup where you're explaining a high-dimensional matrix Y that is observed as a distribution that depends on some latent variable X that is unobserved. And most of these are specified in such a way that the distribution of Y given X is a very standard regression distribution where X explains some parameter of interest that determines the distribution of Y. And because X is latent, it's unknown, we do the most Bayesian thing possible and slap on a prior to do inference. And I think the most famous example of this setup is probabilistic principal coordinates analysis, which is very, very similar to the components analysis. In probabilistic PCA, what we say is that Y given X is a Gaussian distribution that depends linearly on X. What this means is that Y given X is a GP with a linear kernel. So every sample of Y given X will be a plane in this high-dimensional space. And because X is unknown, we slap on a prior. The easier thing to assume is a improper uniform. And if we do maximum likelihood inference or maximum posterior inference in this model, which just says if we try to maximize the posterior with respect to X, then we find that this has an analytical form because we have a linear Gaussian case, everything is super simple. And it turns out to be the case that X, the maximum likelihood estimation of X in this framework happens at the top L eigenvectors of your covariance matrix, YY transpose. Okay. So that's sort of a summary of what the current state of the world is. But there are a lot of different algorithms that are used in single-cell biology that we have no idea if they correspond to probabilistic models. And so these algorithms are the focus of this work, essentially. I'm not going to talk too much about DR tree. DR tree is it has a pretty straightforward interpretation where you just have a linear Gaussian likelihood, Y given X. But the prior on X is a little bit weird. You put on a graph Gaussian choices prior on X, constrained where the graphs are trees, basically. But really, these other algorithms are a lot more interesting because they either are directly used in a lot of single-cell workflows or have other algorithms built on top of them, which are used in single-cell workflows. So really tackling this sort of tackles everything in one go. And it turns out that these fall into two groups, essentially, two broad groups. The top three algorithms, like SNE, TSNE, and UMAP, define a cost function, and this cost function looks like a KL divergence. It is actually a KL divergence. And we optimize this cost function with respect to the latent variables, and we have that as the embedding. So that is the algorithm. We write down the cost function, plug in X, differentiate with respect to X, you minimize the cost, you get the argument, and that is what you use as the embedding. The bottom set of algorithms like multidimensional scaling, Laplacian eigenmaps, and so on are quite different in the sense that what they do is they first set a PSD matrix M to be some function of the data. This matrix M is usually some kind of data similarity matrix, like a covariance matrix or graph Laplacian or something like that. And then they set the embedding to be the top or bottom eigenvectors of that matrix. So just to summarize, it's like you set a matrix M is some function of Y, you calculate it in a deterministic way, and then you set the embedding X to be either the top or bottom eigenvectors of that matrix. And the main work that I've done over the last year and a half has been really to interpret what cost function the UMAP, SNE, and TSNE algorithms correspond to. So those correspond to a very nice probabilistic framework, very trivially. And what I've also shown is that this two-step process of first estimating a matrix and then setting the embedding as the eigenvectors also corresponds to doing inference in exactly the same framework, using exactly the same bounds and cost functions. So that's the very sort of overall broad summary of the work. Anyone has any questions so far? Okay, great. So I will briefly talk about the ProbDR framework, and I'll show how the two-step process sort of leads to the ProbDR framework. But I'm not going to go into a lot of detail to see how each of these algorithms fits. I think the general ideas behind this thing are actually a lot more interesting, and the statistical ideas that underpin a lot of these things are actually very interesting and non-trivial. So I think they're just more interesting to look into. And one of the main hopes for this framework for me is that I really want to provide a framework with which domain experts can build their own models rather than having one big model to set rules everything, so that you have interesting ways in which you can embed prior information that is relevant to your own problems that you're working with. Okay, so just before we go into ProbDR, I'll just briefly go over variational inference, because ProbDR is a variational framework. So variational inference is the way to do inference. You have a model, let's say you have a latent X that goes to Y. This is very reminiscent of VAEs, because this is literally what framework the VAEs operate in. And in variational inference, what you do is you want to do inference over, well, given this model, you want to do inference over X given Y. Variational inference is a way to do approximate inference when you don't want to do other types of inference. So for example, like you could just do maximum likelihood estimation for X given Y, but X is a big matrix and Y is a big matrix, and you might not want to represent the entire matrix and do inference over the entire X. So maximum likelihood estimation might not be the greatest thing that you want to do. MCMC might be ruled out here because, again, there just might be way too much data for you to deal with. And a lot of the times, the sorts of posteriors that you might get from MCMC samplers might just reflect invariances in the posterior rather than interesting information that is coming out of like epistemic uncertainty because of however you specified your model, basically. So you might not super be interested in that either. And variational inference is this other way to do inference where we try to approximate the posterior P of X given Y with an approximate posterior Q star, which has like a nice form. This can be just a bunch of normals for every data point and every dimension. And this Q star is found by doing an optimization process. So variational inference famously transforms the inference problem to an optimization problem. And this is done using, by minimizing a KL divergence between the approximate posterior and the true posterior over the space of approximate posteriors that you can define. So for example, you can just define the space of all approximate posteriors to be normal distributions with means and standard deviations that are free parameters. And you can optimize these free parameters to sort of define that space and just optimize within that space. That's analytically intractable. You can't compute that. So what we do is we write that KL divergence as a constant, a constant minus something else. And it turns out that, because we're just trying to find the argument of that, we don't care about the constant and we just focus on the thing that's left. And the thing that's left is called the evidence lower bound. This is literally a lower bound on the model evidence, which is the constant that we throw away and which is hard to compute. But in certain cases, it's also interesting that this is a lower bound on the likelihood also. So that's a very quick summary of variational inference. And what we do in the ProbDR framework is literally just completely in the slide. This completely determines and describes ProbDR. What we do is we assume a model X to M to Y. So what we're saying is we are trying to explain the high dimensional data Y using latent variables X, low dimensional latent variables X, but through some other intermediate matrix M. This matrix M is a statistic like a covariance or a graph Laplacian or something else that really tries to understand what it is that the salient information about Y that we're capturing is. And this is a variational framework, which means that we specify a variational distribution over the matrix M. So using our data Y, much like in VAEs, we set the distribution of the variational distribution on M to be something, and writing down the elbow and maximizing it gives us the ProbDR inference framework, essentially. So just to recap, we have the model where we're trying to describe high-dimensional data Y using low-dimensional latence X through an intermediate matrix M, where M is some statistic of interest. We place a variational approximation on that random variable M, and we just maximize the standard variational elbow to do inference for X. But the very key difference to standard variational inference, and which is why I wouldn't really call this variational inference, is we do not optimize over the variational distributions. The variational distributions are fixed and they're never touched, basically. So the variational distributions act more as constraints that you bring the model close to rather than the other way around, which is typically done in variational inference. This is not super new. So denoising diffusion models do this, for example. In denoising diffusions, you would set your approximate posterior to be like an AR1 process, and your model is the thing that's parameterized by large neural networks, which you bring close to the approximate posterior that you define. But yeah, this sort of completely describes the ProbDR setup. And as an example, UMAP feeds into this. Yeah.
Sorry.
Yes.
Go back to my slide.
Yeah.
How do you approximate that excitation? How do you draw it?
Drawing samples from this one?
Yeah.
Okay, great question. So the thing is, like, the distribution that is set on M, it just depends on the different algorithm. So for example, as I was about to show in the next slide, in the case of UMAP, M is an adjacency matrix of some graph. And so every element has a Bernoulli distribution, for example. Because this thing is fixed and has no parameters, you literally, it's just a random variable with a set distribution, you can literally just sample from it, like using traditional samplers. So like Torch, you have a Bernoulli distribution set up over this matrix, .sample will just give you a sample. And these expectations can be computed by a Monte Carlo, standard Monte Carlo. So you can just sample a bunch of times and average. Actually, now that you mentioned that, it's an interesting point here is that this term here does not depend on the latence. So if you want to do inference for the latence, and when you want to actually find a latence in the first place, argmax of this literally just becomes argument of the scale divergence. And the interpretation for literally every DR algorithm is just the minimization of that scale divergence, essentially. So you actually don't need this term, but this term corresponds to like a free addition that you get by just slapping on the link from M to Y there. So in ProbDR, although you can interpret the entire framework as just stopping with M, you can just add another link to Y to be able to reason about things at the data level. And you can do this for free. You can do this by just adding a constant to your objective. Okay. So yeah.
The last part of what you did.
Yeah. So like, for example, right? Let me just explain the case of UMAP, actually. So in UMAP, for example, what you might do is you would say this matrix M, this weird statistic, is an adjacency matrix. And the distribution of this adjacency matrix is determined, well, the probability of an edge between 2 points is determined by Euclidean distances, either in the data space, if you're in the variation setting, or between the latents, if you're in the model setting. So what UMAP would do is it would treat the data as one big graph with n nodes, where each node corresponds to a data point, and it would try to put on a distribution on a data similarity graph, basically, where the probabilities of an edge between data points I and j would just depend on like some kind of sigmoidal function that depends on the Euclidean distance between those data points. If you calculate the scale divergence QP in this framework, you immediately get the cost function for UMAP. Like that completely determines the cost function for UMAP. So that's just this basically. And because there's no dependence on X here, argmax of the whole thing is just argument of the scale divergence. So what I was saying earlier was, if we just add this extra bit, which is a link from M to Y, we have a free addition which lets us reason about stuff at the data level, because it just doesn't depend on the latents. It only really depends on the statistic that we are describing through UMAP or through other DR methods, essentially. Does that sort of answer the question, sorry? Or was it about something else?
No, the answer is just I'm a little bit confused because I'm thinking about the data generating process, and you're saying essentially you're given X and there's a semi-deterministic process we generate N.
Yeah.
From N you have again.
Yeah, exactly. It is a random process, right? Like, great question. So essentially, I will come back to this, but the sorts of likelihoods that you can use for the data generating process could look like this, for example. Literally anything that looks like Y given my matrix is a totally acceptable generative model to be using. In this case, because UMAP puts the distribution over an JC matrix, a graph Laplacian is a natural thing to be using there. And a graph Gaussian process is like an interesting generative model that one can use if you only have the graph as the input and nothing else, basically. So you're right, like if you want to sample data, you essentially have to sample first the statistic M and then feed that through the generative model. So it is really weird. And the other really weird thing about this is not marginally consistent. So that's a big boo-boo. It's really like it's a very horrifying like thing here, because if you add new data points to this graph, literally the entire covariance changes. So it's not great. But it is interesting that that you can actually do things in this framework. And really one of the biggest goals for this project is to show that this actually approximates a GP. So even though you are estimating some kind of intermediate matrix M, really the whole thing just corresponds to defining latent variables that sit on some manifold and just using a Gaussian process that is sitting on that manifold to do data generation. Yeah, thank you. Thank you for the questions. Something that I skipped over earlier was the interpretation for SNE and TSNE are super standard. Like instead of defining a distribution on each and every single edge, SNE would just put a categorical or multinomial distribution on each row. So every data point talks with only one other data point, essentially, or in the multinomial case, like n other data points. And really replacing the categoricals with multinomials does nothing to the cost function because it's just a constant that appears. And in the case of TSNE, you just put a categorical or multinomial distribution over the entire vectorized JC matrix. So they really just correspond to different assumptions being put on this graph. And that just determines different statistics that the graph sort of has when you sample from these distributions. But yeah, like I said, one of the main objectives for this was, well, one of the main things that comes out of this is the ability to reason about unseen data. Now, we have to be a bit careful here because of the reasons that I mentioned. We don't have a marginally consistent framework. So really, all of this stuff correctly applies only to the transductive setting, where you have your training data, you obtain an embedding X, which determines the graph that your data lives on. And let's say that you wanted to make inferences about other X also sitting around the latent variables that you've learned. So in this setting, because there's no, yeah.
So I have a question. Yeah. When you make those inferences, you just take the argmax of your method. So if you lose a lot of the granularity that you gained previously for like uncertain cases.
Say again, sorry. When you make these inferences here?
Yeah, so on the 3 slides before.
Yeah. Oh, 3 slides before. Yeah.
Right here, right?
Yeah.
You're just taking that argmax on that.
Yeah. So this is the variational inference, or rather, it corresponds to like a variational inference sort of idea. So with variational inference, what we do is variational inference just turns inference into an optimization problem. And so the argmax just corresponds to that optimization problem, basically. So if we do the argmax here with respect to x is being treated as a parameter, so you don't have a distribution on x, if that's what you mean. But it's essentially, this just describes what the inference method is, essentially. So did I misunderstand the question?
Maybe a little bit. So by taking the argmax and turning it into a discrete optimization problem, don't you lose a lot of the granularity, or say in uncertain cases, right? Just taking the argmax is quite a simple way of just putting a number on it, right? Have you looked into other functions instead of argmax?
Okay. Yeah, so essentially the argmax just comes in because of variational inference, which is to say you do actually lose a lot when you use the argmax in that case. That is a very big simplifying assumption that restricts your approximate posteriors to have a certain form. Really, the best thing to be doing here is to like either fit a normalizing flow to the whole like posterior, or do something like MCMC where you just sample from the posterior. So it is an approximate thing that is happening here. But it is interesting that this is what the DR algorithms correspond to, right? So the DR algorithms, all of the things that I'm describing, have this interpretation. And so if we want to do more interesting things with our algorithms, then perhaps these are the kinds of things that we need to be changing. Okay. So yeah, coming back to this. So we, again, just to reiterate a little bit, we are in the transductive setting where we have some training data Y. We project that to a low-dimensional space to get X train, which determines the graph that the data sits on. And we can try to infer unseen Y values at X locations, X tests that we just define, which can sit around the latents, essentially. And the way that we do this is super standard multivariate normal conditioning. So given this generative model, given this graph Gaussian process generative model, given the full graph Gaussian over the entire space of X test and X train, you can define the graph on that full data set. This is just a big multivariate normal, and using the standard multivariate normal conditioning rules, you can just condition on the things that you see to predict at the places where you don't see. Now, the hyperparameters of this were obtained in this case by maximizing the elbow again with respect to the parameters. And interestingly, as was the case with the latent variables, the first term here doesn't depend on the latent variables. So this literally, when you want to optimize with respect to theta, the only thing you optimize is the first term. So you can first do UMAP, and then you can try to optimize with respect to whatever like generative models that you're interested in, because these things are completely disconnected. So in reality, you would really need to be careful about how you would define generative models, because it is possible that your variational model graphs will have completely different statistics. So a simple way is just use a normalized graph Laplacian there instead of a regular graph Laplacian. But anyway, so if you optimize the elbow, you end up with a bunch of hypers. Plugging it into the standard multivariate conditioning formula gives you predictions at unseen points.
Actually, why normalize graph Laplacian is better kind of avoid the problem too.
Right. Okay. So what UMAP does specifically is when UMAP defines these weird Bij probabilities, they make sure that it's like every data point has at least one edge. And then there's also another hyperparameter that controls for like it's going to be these many other neighbors that this data point is going to have, and everything after this is just going to be set to 0. So it has a very it's a very odd graph that you construct in that way. And then when you maximize the elbow, and when you have a look at the graph statistics that you get when you when you just plug in your optimized X into that sort of model, you see that it has very different statistics. So because there's nothing here that's constraining the number of data points to be, the number of, neighbors to be like 15, for example, there's nothing constraining that. And there's nothing that also says that the probability to my nearest neighbor is going to be 1. So the statistics are very different. And you can end up with cases where you have like hundreds of neighbors in your model, but only like 15 neighbors in your variation approximation, just because that's how UMAP has set the neighbors. And so to not deal with weird sort of cases with this kind of stuff, you can normalize the graph Laplacian. That way, it's like all of the noise levels will be consistent in either case, so on. Yeah, it's like, it is also a weird one because you always optimize it with this with respect to the variation distribution. So everything that the general model sees is samples from the variation distribution and not the model distribution. So there is a disconnect there, which is interesting. Yes. Oh shit, okay. Okay, cool. So that's a quick thing on how you can do inference in this case. One interesting thing here is that if you want to do, I think the other case is inductive inference and not transductive inference, just, pretend that even for white test, even if you append that thing, even if the covariance changes, if you pretend that the hypers will be the same, the stuff still works out great. So in theory, like these things are acting as Gaussian processes. So this X to M to Y setup is acting as a Gaussian process. It acts as if there is some sort of marginal consistency, because even if you pretend that the fact that this is completely useless for inductive inference, it actually still works out great. Like the hyperparameters are still useful, even when you have new data come in, even if the full covariance of the data changes. Okay, so quickly on the other case, the two-step map process, just to reiterate quickly, these are a class of algorithms where you first set a matrix as a function of your data. In the case of PCA, it's super simple, just Y transpose over D. In the other cases, you do some weird centering of kernel matrices or covariance matrices, or you just set the inverse of the covariance to be the graph Laplacian matrix or something like that. And what these algorithms do is they first compute that matrix, and then they set the algorithm to be, so they set the embedding to be the first two or the bottom two eigenvectors of that matrix that I've computed. So what we do in ProbDR is we first interpret the second step to be a likelihood maximization. And essentially we observe that if you have the following models, so if your covariance given your embedding is a Wishart distribution with mean XX transpose plus something diagonal, then the maximum likelihood estimate for X occurs at the top eigenvectors. And this is actually a very simple case of probabilistic PCA. So because probabilistic PCA is defined using normals, YY transpose gives you Wishart by definition. So this just follows naturally. You can also see this by looking at the likelihoods. The likelihood of the normal and Wishart are practically the same. And the second case is what we call probabilistic minor coordinates analysis. This really stems from Chris Williams' work 20 years ago on minor components analysis, and really just flipping the notation and interpreting the likelihood as a Wishart likelihood gives you the result that the inverse of the precision, the inverse of the covariance given embedding, if you set that to be a Wishart distribution with mean XX transpose inverse, then the maximum likelihood estimation, the estimate for X, happens at the lowest eigenvalues. There is a very deep consistency between these results, even though these models are not equivalent. So if I had said that the inverse of the covariance is inverse Wishart distributed with mean XX inverse, those models are consistent, and because by definition they are consistent, but these are not, but they lead to the same solution. So like if you just, because the top eigenvectors of your covariance will be the bottom eigenvectors of the inverse of the covariance. So there's a deep consistency here. So that's the sort of step two. And what ProbDR says is basically we can interpret step one as fixing the variational distribution to be the matrix that we compute. And it turns out that the likelihood maximization can be written as a KL minimization. And in the case of exponential families, which we have here, it's also very interesting that when you do KL minimization, it turns out that so maximum likelihood inference, when you observe some data, is equivalent to KL minimization, where you have the model and variational distributions just have to be the same thing, but where the variational distribution's expected sufficient statistic is set to the data, which is, it's interesting. There's just one more thing there that that is set to be that way. And the last thing I'll mention on the technical stuff is just, if you completely disregard, and this really goes back to the stuff that I was saying about GPs in the other case, is if you completely disregard the variational approximations, and if you just have a look at X to M to Y, and you have a look at what happens when you marginalize M in the setup, you recover GP. And in fact, you recover PCA, which is quite interesting. In both of these cases. So either MCA or PCA both give you the same result. Okay, so another thing that you can do with this is plug in these models into a probabilistic programming language, and you can use the automated inference in a PPL like Stan to just get the embeddings automatically. So I think one of the hopes for me is to show that you can put in interesting assumptions into a PPL, which are domain specific, and get domain specific interesting latent variables out, which are identifiable, interpretable. And yeah, the next steps, which I've mentioned, for me, the main thing that I'm interested in is this connection between the X to M to Y process, and showing that really this is approximately a Gaussian process on a manifold. And we can get away, we can completely disregard variational approximations and say that, like semantically, we are specifying a Gaussian process because we expect that our data is sitting on a hyperbolic surface, which corresponds to my data has a tree structure, or my data is sitting on a hyperspherical surface, which corresponds to my data has a cyclical structure, and so on. So yeah, that's ProbDR. If you have any questions, please let me know. Yeah, that's me.
Thank you very much. Any questions or comments?
When you mention Gaussian process in the hyperbolic process, is it the Poincaré disk that you are?
It is the Poincaré disk, yes. It's in fact the same gene expression data projected on Poincaré disk that shows that you have a lot of undifferentiated cells in the center and all of the differentiated cells on the edge. And actually the angle along this edge tells you what type of cell it is. So this is amazing. Like it's really capturing the fact that your data has a tree structure just by projecting it to that sort of space.
And probably you see it even better if you go to a Poincaré half plane.
A half plane.
Yeah, with the conformal transformation.
Okay.
Because then you can see better what happens close.
Oh yeah, for closer to the edges of the disk. Yeah.
You?
Yeah, I had a question again about the equation that we looked at the whole time, but very bad.
So this one?
Yeah. So you're basically, I'm going to just trying to get an intuition here. So effectively, you're shuffling X around in your to make M like the KL divergent minimum, but you don't parameterize P of M given X have no free parameters except I'm thinking about this non-parametric. Right? So you're effectively shuffling around X, but you're not altering the distribution at all.
No.
Exactly.
Yeah.
But what you are doing is then you're altering with this additional term, which is parameterized, the likelihood is parameterized by theta.
Yeah, exactly.
Why doesn't the first generative model, because it feels like I can totally see in the interpretation of doing what these algorithms do, but it seems like you're going to get a very peculiar solution because you're doing this stuff.
It is a very peculiar solution. Yeah. That is what you find. So in the UMAP cases, for example, what happens is because X is unconstrained, X has a improper uniform prior. The sort of graph statistics of what that looks like determine the samples that you get a lot, like really, really a lot. So the distribution of X, for example, if you have a uniform distribution, you'll have like a uniformly connected graph in some sense. If you have like a Cauchy sort of distribution on X, you'll have like a really like very connected center where the function is completely constant because that's the only thing that corresponds to like a very connected graph. And then outside it can do whatever. It can be super weird.
So that is basically the thing that encapsulates this deterministic step of calculating n, right?
Yeah.
So but that would make sense to actually, well, I don't know what model it would now correspond to, but if we would actually parameterize P as well, right?
This one?
Yeah, because Q is fixed, right?
Yeah.
Q is fixed, but you would give the distribution from parameters as well, right?
Yeah, it's interesting. The thing is, my intuition for all this is the specification of the variational constraint is so like constrictive that is what's determining the quality of things that you're seeing. And yeah, the sort of X to M to it's so free. It can do literally whatever. So yeah, there's a lot of like capacity there for constraints.
And actually, can see the question, GNN, right? And maybe GNN is not going to be a P.
Oh, it can for sure. Yeah, literally anything that you can put on Y, which looks like Y given a JC matrix, is totally fine as a generative model. In fact, I think the graph Gaussian processes are also interesting because, and I think Felix has done some work on this actually. So if you think of the simple graph convolutions, they are essentially just one layer Gaussian process predictions. So like GNNs would be like a deep Gaussian process sort of interpretation or something like that.
More questions or comments? Okay. Thank you very much, Aditya.
Very glad if you have any questions. So.